Welcome to example number 10. In this case, we have a dart gun that's being compressed, um, and the dart is being fired off with some final velocity Vf, and we're asked to find out what is the muzzle speed, which is basically what is the speed that the dart leaves the dart gun. Okay, I'm going to use the modeling approach again to solve this problem. So we'll first start off by using our energy bar graphs here. So go ahead and create an energy bar graph and also decide on what you're going to consider as your system. Okay, so here we go. We have our system in the circle, and I will decide to choose I don't know, the dart gun, the dart, the earth. All right, now the dart gun would include basically the spring into our system. Huh? Okay, so we have the dart gun or spring, the dart itself, and then the earth as part of our system. Now, the dart, I guess, is fortunately for us, is being fired horizontally, which means that it would probably be consistent to choose this particular point right along this dashed line to be our reference level height. Let's just choose that y to be equal to 0, therefore making our gravitational potential energy 0 both initially and finally. So this is our before picture, this is our after pictures, right? So by the way, this is going to be our before energy bar graph, and this is our after energy bar graph. Okay, so we've just eliminated the fact that there's no gravitational potential energy just because it doesn't go up at all and it stays at the same level. All right, so what kind of energy do we have in our system when the dart is being compressed this distance of 8 centimeters to the left? And remember, it's not moving. So if it's not moving, it doesn't have any kinetic energy. Remember, 1/2 mv squared is kinetic energy, so no velocity, no kinetic energy. But it is compressed. There is spring potential energy, which is 1/2 kx squared. It's being compressed this distance of 8 centimeters. So we definitely have spring potential energy. So let's go ahead and show that bar in here. This is our spring potential energy. And then when the dart leaves, it goes back to the being at the original length, so it's unstretched now at this point. So there's no more spring potential energy in the spring. And so we really only have now this moving energy, which is called kinetic energy. So what happens to this bar now? Now all of that energy has been transformed into kinetic energy. So now we can then proceed to use our conservation of energy statement. So we're going to start off by saying the energy before is equal to the energy afterwards. And there's no work done because we kept the dart, spring, everything, earth into the system. So we have initially the energy is just spring potential energy, and at the end we have just kinetic energy. And our spring potential energy is given by 1/2 kx squared, and our energy at the end is going to be kinetic energy, which is 1/2 mv squared. So now we can start to substitute. By the way, I see a half and half on each side. Why don't I just cancel those out? And let's write down our known information, our given here. We know that the spring constant K is 400 newtons per meter, which that tells me I have that now. I know that it's being compressed a distance of x equals -8 centimeters, but I need to convert that to meters. Remember, this is newtons per meter, and we want energy to be in joules, so that should be -0.08 meters. We also have the mass of the dart, which is given as 20 grams. But that needs to be put into kilograms. Remember, we have to have our energy in joules, so that's going to be 20 times 10 to the power of -3 kilograms. So now we're ready to substitute in here. Let's just rewrite that over here. So we have kx squared equals mv squared. K is 400 newtons per meter. X is a -0.08 meters squared. And then we have their mass, which is 20 times 10 to the power -3 kilograms, and then our velocity squared. Solving for v squared, we're going to get that equal to 128, and then v would be equal to the square root of 128, and v would be approximately equal to 11.3 meters per second. And this is, by the way, a conservation of mechanical energy because we are assuming that there is no friction, so we're not losing any energy out of the system in the forms of heat and so forth. All right, that's it for this example.